Well, thank you for coming again. To begin with, I will talk about the domain where I study the problem, which is a smart home. You know, the smart home is a home that is full of electrical devices, sensors, actuators, things like that. And they cover many multiple domains, like security, healthcare, and comfort, games, energy efficiency, etc. The devices we find are connected, are easy to install, at least nowadays, and are affordable. To cite some, toothbrushes, scales, locks, fridges, all connected in the home. And often with these applications, we find bundled many applications. With these devices, we find many applications that are bundled. This is why the Home Gateway initiative conceives the home containing a smart home gateway or a home automation gateway, which will host all the applications running and give access to the devices at home and to the internet. This will enable reducing the costs of deployments of applications, and it will enable easier sharing of the devices between the applications. Before I start my explaining of the problem, I need to explain my hypothesis. The evident things are that applications are full of bugs, or at least buggy, and they also can be malicious. Especially that in my context, I don't trust application providers. I don't trust them. I mean, I don't suppose they are reliable. The platform, that is the Smart Home Gateway, is a long-running platform. I expect this platform to run for at least months. And an abrupt restart of the platform can be dangerous because this platform can control things that are very vital or very dangerous to contain, like gas valves, for example. And restarting the platform in the middle of such operation can lead to leaks, which can form hazards for the inhabitants. So first, the problem. What is a stale reference? A stale reference is a reference to a stale object. And a stale object is simply an object that should no more be used. These objects frequently appear when applications are uninstalled or updated in OSGi, or in general in very dynamic applications. So if we see here a reference from an object O1 belonging to an application app1, referencing an object O2 which belongs to another application. In installing the application 2 makes O2 stale, which evidently makes the reference to O2 also stale. Now you should tell me, okay, but why this is a problem? This is a problem actually because the virtual machine cannot remove O2 from memory. And this itself will have more negative consequences. To illustrate the thing, this is a typical application of an alarm application that gets its data from a gas sensor. So if you have a gas leak, the gas driver will notify the alarm application, which will ask the siren driver to make the loud siren or something. The siren driver uses a siren configuration, which contains things like the ringtone, loudness, things like that. And it's in a simple text file. This is just for illustration. We will illustrate here a scenario that will make a bit more visible the consequences of stale references. So first, we will update the siren driver to another version, to version 2. And this update will migrate the siren configuration to kind of more rich configuration file in XML file format. And we will forget to update the reference held by the alarm application to the siren driver. Because normally, when you update an application in OSGi, everyone in the platform, or at least everyone that is interested, will know that the siren driver was updated to version 2. So normally, the alarm application should update its reference to version 2. We forget to do it to illustrate what is a stale reference. In fact, what happens is that the reference becomes stale because siren driver 1 has been uninstalled. It should no more be referenced by anyone. And the siren driver will need to stay in memory because the Java virtual machine ensures that any object that is reachable must stay in memory. So there is a memory leak here. The second thing is that if for any reason This siren driver, due to a request from the alarm application, needs to rewrite its configuration here. It will override the migrated configuration that was done when the siren driver was updated. So this is a data corruption. This is just for illustration purposes, but it could be worse. There is another problem also, that is, in this case, if the gas sensor sends an alarm to the alarm application, the alarm application will try to put on the siren to make loud noise, but this won't happen. Why? Because the siren driver version 1 was disconnected from the alarm siren because it was uninstalled before. And therefore, there is no way for the alarm application to make a sound. The alarm siren will stay mute, and the danger will be there. To make it more clear how significant the memory leak that is caused by state reference, we need to see the graph of objects in Java. In Java, any object references its class, and every class references its class loader, and every class loader references all the classes it loaded. So basically, if an object O1 retains a stale reference to a stale object S, this will retain in memory everything here. This contains data, static data, Java bytecode, and machine-generated code, which is a huge amount of memory. To illustrate how the evolution of this happens, this is just a small test that re-updates or updates continuously an application containing one stale reference. The updates here, illustrate that the memory leak is almost linear. Whereas when we use the Incinerator, which is the solution for this, or my solution for this, we get a stable memory consumption, which means that the memory leaks are no more there. So the approach of Incinerator, explained like this, is fairly simple. Incinerator will just look for all the stale references, that is, all references to stale objects, and will transform those references to null references, so that any access to them will result in a null pointer exception, and it will be visible. There are two problems basically with this approach. The first one is that we do this to clean up memory, so we need to take special care when we deal with finalizable objects. Finalizable objects are objects that implement the finalize method, where they need to clean up something when they are no more reachable. The problem is that if you attack those objects with Incinerator, the finalization method might get null pointer exceptions if it tries to use stale references. So in order to avoid that, we just defer the finalization approach until the next garbage collection. That is, we don't touch those objects, we leave them alone. When they finish finalizing, we will try to see if there are more stale references in them. So when Incinerator sees something like this, that is a finalizable and unreachable object that is using a stale reference, which should be eliminated, it will just defer that. The second major problem with this approach is synchronization. Imagine 3 threads that synchronize on an object, and then that object becomes stale. And then we have simultaneously many stale references appearing. The problem with the approach is that if we eliminate those, then this will happen. The thread 1 will continue running, and the thread 2 and 3 will be blocked forever. Why is that? Because they will have no more access to the object, thus no more access to the monitor of the object. And then T1 cannot notify the monitor, and T2 and T3 will be blocked forever. It's just a dead block, an artificial dead block that is caused by Incinerator. So the approach we do is that first Incinerator will remove the reference held by the active thread. And it will, of course, the active thread will get a null pointer exception if it tries to access the monitor or the object itself. Then Incinerator will mark the object or the monitor of the object as stale, and it will wake up one other blocked thread. It will do the notify itself. When this happens, the thread T2 will wake up in the monitor acquire method. The monitor acquire method is when is where the thread gets blocked when it tries to access the lock of the monitor. When it does so, the monitor require method that we modified will remove the reference to S1 and will wake up the next blocked thread and will launch a null pointer exception to indicate that the monitor could not be acquired because it's a monitor of a stale object. This will happen in a very cascaded way like this until the last thread gets woken up. It will do exactly the same thing. It will launch a null pointer exception to indicate that it could not lock the object. This way, all the references from the thread disappear. The threads will continue running if they handle the null pointer exception, and the object, the stale object, will disappear from memory. Our implementation is around 1,000 lines of C++ in an experimental JVM, that is the G3. We tested this on the Nupperfish implementation of OSGi. We just have to add 10 lines of Java code to the source to support our tool. And it's basically due to a limitation in the OSGi API. Maybe one day that would not be the case. Our implementation is independent of the algorithm of the garbage collection. It happens because it doesn't depend on that algorithm. And it's open source on the site of llvm.org. We did some functional evaluation, and we compared that to the verbatim G3 or the hotspot JVM, which has no support for stale references. And honestly, this is very normal because stale references do not appear that frequently in Java. They are caused by OSGi because of the frequent update and the very easy reuse of objects that is made by OSGi. It can theoretically happen in any other platform that uses the class loaders to represent applications and unloads those class loaders the way OSGi does. And it can even happen in other languages like C# or anything. In general, it can happen in any language where the automatic memory management guarantees the existence of an object if anyone holds a reference to it. So we compared it to the verbatim JVM, which obviously doesn't detect any stale references. And generally speaking, developers also cannot. In fact, it can only be detected when it gets too huge, and developers will begin to see an abnormal usage of memory that is higher than normal. We also compared that to the previous state-of-the-art tool that detected stale references, which is Service Coroner. Service Coroner uses aspect-oriented programming to monitor the OSGi API to see what are the objects transferred through it, and to monitor when these objects become stale, so when they should be removed. So obviously, Service Coroner can only detect one scenario, which is the scenario of objects that are visible from the OSGi layer. All other objects that are not visible from OSGi are not detected. Objects that are in local methods or in static fields and object fields, etc., are not detected. Synchronization is not detected also, and finalization. Finalization here, I mean the objects that implement finalize and that use stale references. And even more, Incinerator doesn't only detect those references, but it also eliminates them and makes them visible to the developers. By the way, in the OSGi specifications, stale references are recognized as a problem, but are left to the developer. We performed some performance benchmarks using DaCapo benchmark suite, and we had an execution cost of less than 4%, which is very acceptable for testing environments and production environment on the long term. So to conclude our talk, we presented here Incinerator. It's a subsystem inside the Java virtual machine that enables us to detect and eliminate stale references so that to avoid memory leaks, data corruptions, and physical hazards. And it makes stale references visible through the null pointer exceptions so that applications that have them can be debugged at runtime. These bugs can appear and can be fixed even in production environments because the cost is less than 4%. And the implementation is mostly independent of the OSGi framework implementation and also of the garbage collection algorithm. That's it for Incinerator. Thank you.
Any questions?
Yes. Yes?
I'm not exactly sure if I understand what a stale reference is. Is that like a service reference to an object? Or can it also, because you can also have an actual reference to the object, right?
Okay. So our question is a stale reference a reference to a service?
The service reference. Okay.
The service reference.
Or to an actual object.
Okay. The answer is it is a reference to any kind of object in Java,
Okay.
be it a service reference or anything else. In fact, if it's a reference to a service object, then service coroner would detect it because it would be visible from the OSGi layer because it's OSGi, it's the OSGi API which gives that reference. But it can be anything else. It can be, for example, an object that you got by calling a method of a service. Okay. Mm-hmm.
Right now, if I get it right, you modified the G3 experimental GVM.
Mm-hmm.
Is there also some research being done on implementing like an agent and making it more available for even OpenGDK, for example? Or is
Yes,
too
it
hard
is.
to plug it into the
In fact, I am actually doing that right now.
Oh.
But because I finished my PhD already, this is a pet project. I'm doing it on the hotspot JVM. So on the Oracle hotspot JVM. And I can say I finished like 70% of the work. I still have some synchronization issues to do. And I'm not implementing it as an agent because I need more access to the JVM than just what is given using the JVM-TI API. So I'm implementing it inside the JVM itself. I am using the hotspot 8. And by the way, my work it's not finished, but it's already on GitHub.
I got a question. So, what is it that you would like to change in the OSGi specifications, if anything, to make this problem easier to solve?
In fact, I would not change anything in the OSGi application API. I would rather change something in Java. The problem with this is that what I am doing is just an artificial way of transforming a strong reference to a weak reference. I don't know if you got these principles. In fact, a default reference or a reference you use to access an object is called a strong reference because it holds strong guarantees on that the object will stay there. A weak reference will enable you access to the objects, but will enable also the garbage collector to get it in at any time. What I'm basically doing here is that I'm transforming a strong reference to a weak reference when an application is updated or uninstalled. I'm trying to combine the state of applications, which is an OSGi concept, with the nature of references in Java, which is a Java concept. There is no way of doing it like this in Java, in a way that is compatible with the language, because here I am modifying the semantics of the language, because a strong reference should not be modified by anyone except the application developer. I am doing it here because I am putting null there. The thing that I can guarantee, though, is that this will not touch any applications that have not stale references. An application that do not access stale reference, even if it holds the reference but does not access it, will not see any behavioral changes. So maybe what should be done in Java is that somehow we should be able to transform the type of reference at runtime. That is, transform a reference from a strong one to a weak one. This would make such a tool, at least the implementation, very easy. But at the OSGi layer, I don't think there is something to modify because it's not really it's not due to the OSGi implementation specification. It's due to the implementation because OSGi implementation uses class loaders. If OSGi could invent some other way to make dynamic applications in different way, not using class loaders, I think this problem would disappear, or maybe it would reappear in different form. Depends on the implementation.
Just one more question.
Yep.
Right now, the white elephant in the room is we're talking about stale references, but how do you consider something a stale reference? In OSGi, you say it's from a bundle, so that everything related to the bundle is now stale. If you would move that to general Java, you would also need to make an abstract concept of these things belong together. Have you already worked out a framework for that to see, or is it just you're mostly working on data right now for making it work perfectly well in OSGi, so maybe it's still abstract.
So if I resume the question, is this OSGi specific or Java specific? That's it? Is my implementation is OSGi specific or Java specific? In fact, inside the JVM itself, there is just one small class that is specific to OSGi at all. Everything else uses Java concepts. What I hide from you here, because it's implementation details, is that I mark class loaders as stale. Because if you can find this in my PhD if you have time, but a stale object, a stale reference is a reference to a stale object. A stale object is an object that was created by a class that is loaded by a stale class loader. In everything here, there is no OSGi. There is just class loaders. This is how it is implemented. The small class I told you about that is in the JVM is just a bridge between the state of applications in the OSGi and the state of class loaders inside the JVM. So this is maybe like 5% dependent on OSGi. And it's very decoupled. So even if you use another technology that uses the same method of separating applications using class loaders, you can reuse this.
In theory, an enterprise Java server could just mark
Yes.
class loader stale and then your framework.
Exactly. Exactly. Any other questions? Yep.
Yeah, would it be possible to have it thrown a different exception in case a stale reference is accessed, like stale reference access exception or something, which is more discernible from null pointers, which can also appear due to other bugs?
Yes, I understand that, and we also tried to look at the problems. In G3, theoretically, no. I can give you why if you want. If you want, I can give you. Okay. The problem is that when you access a null pointer exception, you are accessing an address that is inaccessible in the user mode. When you compile Java code, references become addresses. So when you try to access an address that is a null address, you will get an exception. And that exception will be handled by the JVM to form a new exception object and give it or raise it on the application. The problem is that the null pointer exception is not just address 0. It can be, for example, address 4. If you are trying to access the second or the first field of an object, because when you access the first field of an object that is null, you will access address number 4 in 32 bits. So access to address number 4, for example, or 8 or anything like that, addresses below 2 gigs, generally speaking, you will always obtain a null pointer exception. Null doesn't mean 0. Okay? Null means that the object is inaccessible. The problem is that we could not figure out how to give a special address to the stale objects or stale references, so that we could not replace a stale reference by something very special that indicates, no, this is not a null object, but a stale reference. How to say it? this is dependent on the implementation. And unfortunately, G3 uses this way, which is a very fast way, it's for performance reasons, to know which is a valid reference from a null reference. The hotspot JVM does the same. So if you want that, you would need to mark the address or to use some special addresses in order to be able to distinguish a null pointer exception from a non-null one. I had an idea, but I didn't implement it because this is syntactic sugar. The idea is what? Use unaligned addresses. You know, we are working in 32-bit world or 64-bit world. You can never find addresses at 1, 2, 3. They are always aligned. And this is all addresses are like that, guaranteed. So if I could put the address number 1 there, that could not be an address of anything, actually. Even if you added something to it, it could not be an address that is formed normally from a valid reference or from a null reference. Because even if you put a null reference and you add something, an offset, to access something in the object, the offset will always be aligned. So if I put a non-aligned access and you add something to that, it will be always non-aligned. So I could try to use that trick to know that this was a stale reference, not a null pointer exception, not a null reference that originated from something else. This have some applications is that it will make your CPU unhappy because CPUs generally hate non-aligned access. So it might be a bit slower in raising the exception, but such an exception should not be that frequent, so it should be okay for the cost. But I didn't implement that, not for now. Yes?
I wonder, like, this must be a known problem for Java in general, especially with things like Jigsaw coming up.
Mm-hmm.
Is there any effort on the JVM side to somehow
To implement that?
Yeah.
Not for now, as I know.
Okay.
I didn't contact Oracle for an implementation of this. I'm trying to do it myself for fun now because my PhD is finished. Maybe one day, if I have a working prototype on the hotspot 8, they could re-implement it or make it somehow in their production products, their production solutions. But for now, no.
Any more questions?
Well, thank you very much.
Welcome.